This video explains a little bit of analysis of MIDI files using the R tabr library and tidyverse. So let's get started. We want to load our libraries. So we'll start with the tidyverse library and the tabr library. And I have a bunch of MIDI files that I'd like to show you. I've aggregated them up from various places. Helpfully, the tabr library has a read MIDI function. Takes a few moments to load a MIDI, but it certainly can handle large MIDI files as well as small ones. So here I'm going to load 3 different MIDI files for you. Oops, I'm overwriting my MIDI file. Sorry. There we go. Oops. There's 2 files and 3 files. The first file is a file I got off the internet, a MIDI file of Bach's Prelude and Fugue, number 846. And the others are 2 improvisational piano pieces, both recorded on an electric piano that we have. The Improv was also passed through an online MIDI converter. Improv 2 was recorded directly off the instrument. If you take a look at what's in a given MIDI file, you'll find that there are quite a bit of pieces of information. They come in events, and there's a variety of events that are present in a given MIDI file. It is interesting enough to ask what MIDI files events are present and what their prevalence is across files. Let's have a look. A good way to do this is to put everything in a single data frame, add in a new column for each of the different files so that you can see which is which, and proceed. So the way to do this, let's take a quick look at one of these data sets to see what we've got going on. So these are all the MIDI events that are present in the Bach file and the Improv file. You can see different events are present. So we'll add another column to each of these. You can see each of these are 12 variables each. They have the same variables. So we can add a 13th variable that discriminates the name, and then we can stack them all together. The way to add a name column is just with the mutate. So we can take the Bach file, add a new column called name, and we can tell it that name ought to be Bach. Okay, sounds good. But now what we'd like to do is we'd like to then stack all of these guys together. So how to do this? Well, I'm going to stack them all into a single data frame called songs. And I find it a little bit convenient not to pipe things, so I'll do it like this. So that's our first mutate, but now I want to stack these guys together. The way that you stack data frames on top of each other is with the bind rows command. And then just do the same for each of the other pieces. And there we go. Now we've got one big data frame of 13 columns, the 12 columns that were originally there, plus a name column. And you can add up all the number of observations and find that, yep, that's the right number of rows there. So now we can conveniently make a nice table by doing group bys. So we can group by the name, and we can count up the different events and see how many there are in different songs, except for the fact that I spelled songs wrong. Okay, except for the fact that this isn't so convenient because it ran off the bottom of the page. You can certainly view it. I find it convenient when displaying tables to pivot them. So if you have the data in a tidy format, and want to render it as a nice table for human reading, it's convenient to pivot it out of that tidy format. Notice the count function produces an n column, so we'll pull the values from n. And I can't spell pivot correctly because it's pivot wider. There we go. And, wow, names from, values from. There we go. Okay. And so we now have each of the events enlisted with their prevalences across the different files. You can see that the prevalences vary quite a bit. So for instance, only the Bach file contains text events or copyright notices, but the other files have most of the other features. The controller, for instance, is something that the online converter, the improv, the middle column there, removed, whereas the actual instrument kept the controller events there. The Bach only had some of the controller events, so probably every note produced by our piano has a controller event to set some settings of exactly how that note sounds, whereas in the Bach piece it only happens when there's a specific reason for it. That's just a guess. You can do the same kind of analysis with others. Rather than events, you could certainly look at things like the tracks. And you can see that the Bach piece has one track. Everything's in track number 1. Same with the Improv 2 piece. The improv piece alone, which passed through the online MIDI converter, has 2. There are plenty of other columns that are present that you could examine. Times, lengths, durations, types, etc. Although some of these are a little better viewed not as a table, but rather as a plot. Easy enough to tweak that. Instead of doing our pivot wider, we could certainly go ahead and plot them. We've got our group by, and we can just pipe this right into a plot. So for instance, if you're interested in what this parameter 1 guy is, you can do something like this. And there you go. You can see that the different pieces have different values of the parameter 1. If you're interested in zooming in on one of them, say for instance we're interested in seeing what happens with Bach with that particular parameter 1, we can filter it out. And maybe instead of name we do time. Indeed, as it happens, parameter 1 has something to do with pitch. In fact, it is the note number, the MIDI note number for each note. Now, it's convenient sometimes to just pay attention to a specific set of events. Only, for instance, the note on events. At a simplified view, you just need the note on events to kind of understand what's going on. So, for instance, we could say, I'm just interested in understanding something about the note on events. How do you do that? Well, a filter will handle that rather nicely for you. You can say filter event equals note on. Watch the capitalization. And if you do this, we get basically the same plots we had gotten before. Because, in fact, these warning messages that showed up here were for all the events that were not note-on events. So if we go look at time, and we look at parameter 1, and let's say color is equal to name, you get each of the different songs, and you can see the Bach piece is quite a bit longer than the other two. There's a bit of over-plotting going on here, so it's a little bit misleading, but it's not too bad. Okay, well, you might ask, okay, how do I know that note-on events and note-off events are really the same thing? Well, check this out. If you compare the note-on events, or look at the note-on events, you'll notice they have durations. So, for instance, this note-on event here has got a duration of T32. That means it's probably a 30-second note, and it's got a length of 42 MIDI time units. If I add 42 to 44, what do I get? I get 86, and look at 86, there's a note-off event. So in some sense, just from a simplified point of view, the note off events are redundant. They're not completely redundant, but they're kind of redundant. The MIDI controllers can pack additional information into the note off events that you'd be losing if we get rid of all of them. But this kind of thing suggests that maybe we want to check that. You'll notice on our table here, the note on events and the note off events, we got the same number of each. So it kind of suggests that, that they're related and paired. Let's take a look. Let's take a look at the note on events, and let's make a new column, which is the note end time, so we can compare that. Well, that should be the time column plus the length column. And let's just pick out the note end column that we just created, because otherwise things get a little too busy. And let's sort these. Okay, so those are the note ends. And then if we take this songs filter and we just filter out the note off events, and instead of selecting the note ends, which don't exist for these guys, we just pick out the times. Oops. We get the same, in fact, set of numbers. So 86, 103, 130, etc. So that pretty much confirms that we're dealing with, if we just keep track of the note on events, we won't lose that much. We'll lose some for sure, because there are additional metadata present. But hey, that's not too bad. Okay, one thing that's convenient is to take a look at is to look at what amounts to a piano roll. That's kind of what we've got going on here. This is what you would instruct the instrument to play. If we focus in on one of these songs, so I just had my plot up before, this guy here, let's just focus in on one of them. In fact, I can add my filter here. I could say name. So just filter in just one of the pieces. You can see that there's definitely two frequencies here running. In fact, it's convenient to pick this Y to be the pitch. And you can see the pitch listed by letter. The parameter 1 versus pitch, how are they related? Well, they're kind of related because the parameter 1 translates into a pitch, but also translates into a frequency. Well, it's convenient to translate the pitches into frequencies. Tabr can do this for us. We can add a new column for that very purpose. So let's make a new table, songs notes. We'll pick out just the note on events. And let's use the tabr function as music df. What that guy does is that supplies a whole bunch of useful information, frequency for sure, and lots of other things. We'll feed it in the pitches, and that it'll do the rest for us. And let's add the end times, because we know now that those are already present in the note on events, but they're convenient to have on hand. I think that looks right. This takes a little while because the asMusicDF function is not particularly fast. But there we go, we've got it. So now if we go ahead and plot our events, we don't no longer need to filter out the note on events. We don't need this group by either, because we're just looking at one song. But now we can look at parameter 1 is the frequency in hertz. And we don't need the color either. And there we go. So this matches up with the parameter 1 pretty closely, except that it's been stretched. There's a log scale involved here. Easily fixed. And that looks pretty much like the parameter 1 plot that we had up before. Pretty neat. It might be convenient to try to color this based on how hard the keys were hit or the velocity. You can see some of these keys are hit harder than others. The darker ones are hit a little more softly. Okay, you can now ask yourself, well, all right, what key is being used here? Well, it's convenient enough to ask that question, and it's not too hard to make use of what we talked about in the previous video with the is diatonic function, which tells you whether a note might be consistent with a key. It's not fully conclusive, but it certainly is worthy of trying out. How do you do that? Well, we want to apply the is diatonic function to each of the notes in the pitch column. The problem with this, if we take the song's notes and we were to ask for the is diatonic, so we can select out the pitch. These are the pitches. So just so you can see, there they are. You'd really want to do something like this. You'd like to say, pipe that right into is diatonic and tell it key is equal to whatever key we think it might be. Is this in key C? And it says, I don't like you. The issue is that is diatonic is not vectorized properly. This could be remedied by forcing it to vectorize with the map function. And then when you do that, you do map, put in a tilde to say that this is now a formula, and map expects that the first argument to this special function is .x. So there, we've now put that in. And now this is going to give us a list of whether each note, list of logical values, trues and falses, for each of the keys. It's chugging along, doing it for all the songs, and this is not particularly fast. Okay, there, it did it. A whole bunch of trues and falses and such. Looks like, generally speaking, mostly consistent, but this is across all the different songs. We could just pick out a single song. For instance, this one here. Oops, missed another pipe. Okay, looks mostly like true, doesn't it? With a few falses thrown in there. You could ask for this to be counted. That's pretty straightforward enough. In fact, it's convenient to drop this in as a new column called key check. The way to do that, of course, how do you add columns? With mutate. So you can say mutate key check is equal to this map. And then we can count it, because now it's a column that we can count. For instance, you can say, find me all the key check equals trues. And what did I do wrong? Right, mutate wants to know what I'm supposed to take as input. I'm going to put that is input rather than just selecting out one. I'm now adding to my columns. Okay, and it finished, and basically you can see the vast majority of these notes are indeed in the key of C. Incidentally, the musician who played this piece, this improvisational piece, informed me that this was played in C major. So this seems pretty consistent with that. Well, that's what I wanted to show you in this exercise. Hope you enjoyed it and maybe learned something. See you next time.